I'm ready to move on to the transmitter now, and the construction's pretty simple. But before I do that, I thought I'd talk a bit about the bandpass filter formed by inductor L12, which is right here, as well as these four capacitors just above it. So I've got above here a close-up of the bandpass filter arrangement, and it really is quite ingenious. The FST3253 here is used in its classic role as a switch, and X5, which we probed before, basically is this 2-bit control for the switch. So the way it works is these 2 bits here, B is the most significant bit and A is the least significant bit. These 2 bits control which one of these and which one of these gets connected to Z and W respectively. So for example, if the 2 bits are both 0, then what that means is that basically Y0 and X0 will be connected to Z and W respectively. If the 2 bits are 1 and 1, then what that means is that Y3 will be connected to W and X3 will be connected to Z. So if we have a look, say, at 20 meters, so for 20 meters both bits A and B are both 1, what we'll have is, this is from the LPF here, and for bits 1 and 1 set, that will connect Y3 to W and X3 to Z. So you can see the LPF will come in here, pass through this 22 picofarad capacitor, off to pin 9 here, and then back out through the inductor L12, and then back in through X3, and finally out through Z and through to the splitter. So you can see that in the 20 meter arrangement, you have the 22 picofarad capacitor and 19 turns of the of L12. So I've got some more detail here. So the example we just went through is the 20 meter. So similarly for 80 meters, that connects in series the 220 picofarad capacitor together with all 41 turns of the of L12. And I've measured L12, this is through with my LC meter. You can't just use like toroids.info to calculate it, because these 19 turns are all squished together on the toroid, so they actually provide a greater inductance than would be estimated by toroids.info. So you can see here the first set of 19 turns yields 2.9 microhenries. Further 30 turns yields 5.3 microhenries, and the second to final one is 7 microhenries, and then the final full 41 turns is 8.6 microhenries. I calculate the resonant frequency of that in-series arrangement. This is the classic formula, F equals 1 on 2 pi root LC. Now, the interesting thing is for 80 meters, it's close. But for 20 meters, at least the calc that I'm showing with 2.9 microhenries and 22 picofarads shows it way out. Now, I've actually tested this. I replaced the 22 picofarad capacitor with a 47 picofarad capacitor. It made the situation worse. So the setup in the radio is correct. So what I'm guessing is I'm missing out on some capacitance somewhere else. I don't really know where that is. I've had a look around the board. There's nothing in there. I did try and simulate with LT Spice the effect the LPF has, and it had almost none on the resonant frequency. The only thing I can think is maybe there is some sort of stray capacitance in the diodes that form the switching arrangement in the LPF. So anyway, that's my theory. I thought this might be of interest. I do think the LPF is quite ingenious, and as I said, I did try changing those capacitances and it made the situation worse, so they're definitely the right values. But anyway, that's a little diversion. Let's get back now into the transmitter. There's a few bits that we have to put on the board, and let's have a look at those now. Okay, so here's a close-up of the board, and let's just walk through the components that have to be installed. So we have this L14 here, which is an RFC coil. we have this binocular core here, which needs to be wound appropriately. Now, what the manual says is if you're using 9 volts, then it's 3 turns and 3 turns. If you're using 12 volts, it's 3 turns and 2 turns. So different amount of winding depending on whether you're using 9 volts or 12 volts. I will wind this for 12 volts, so that means 3 turns on the primary, center tapped, and 2 turns on the secondary. And then the final thing that you have to install is this array of 4 BS170s FETs right here. Now they're installed here, 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 and here, and they're also installed face down. And then you put this washer and a screw with a nut on the reverse of the board. And it uses the board as a heatsink. So what we'll do is, I won't go in detail on the RFC. That's pretty straightforward. That's just 10 turns of the 22 gauge wire on a T3743. But we'll go in a little bit of detail on this one. This does have a center tapped arrangement, so it's not tricky, but it's an interesting little wind together. And then I'll finally get these installed and we'll be able to test transmit. Okay, so we're getting ready to wind T1, which is wound on this binocular core right here. And as you can see, I'm going to use 12 volts, so it's going to be 3 turns to 2 turns. If you were using 9 volts, it'd be 3 turns to 3 turns. Now, the interesting thing about the 3 turns on the primary is it's center tapped. So there's instructions in the QDX manual. They're a little bit different to what I'm going to do. And what I'm going to do is, this is going to be my construction of the, whoops, it's fallen out there, my construction here. And what I've got is 2 pieces. So this side is going to form the 3 turns. And I'm going to center tap this by removing the enamel from the ends here, and then soldering these two guys together. Anyway, just goes to show there's many ways of skinning a cat. So what I'll do is I'll remove the enamel from both sides of this. I will solder them together, and then we'll come back. Okay, so there's the construction there, and you can see there's a really good solder joint between the main set of turns and the center tap. So what I'll do now is I'll wind that around the binocular core. Okay, so this is going to be interesting behind the camera here, but basically the way a binocular core works is every time both go through the center, that's 1 turn. So there's 1 turn. Now let's turn this around and do turn 2, which is both of these wires through the center. Making sure I'm still in camera here. So there's 1. Make sure to keep it nice and separate. 2. So that's 2 turns. Keep it nice and tight. And then we've got the final 3rd turn. Make sure I don't scratch the surface there. And then the final turn on the other side. Okay, so there we go. There's the finished center tapped toroid. Wasn't too painful. I wish that this wire was a little closer in here. But anyway, so now the next thing to do is get the enamel off here and here. As you can see on the other side, the enamel's already off. So I'll come back and do that. So there's the finished product there, well, at least the 3-turn side. I've got to wind the 2-turn side in. And with an even number of turns, you push it in the same side that you want it to come out. So 2 turns, we push it in this side. Hard to do this behind the camera, believe me. So push it in there and there. Bear with me. All right, that's in. Alright, pull that through, make sure it's nice and tight. Let's get it away from that. So that's nice and tight there. And then turn it around and complete the second turn. Sorry for the out of focus here. There's one turn, and here's the second turn. Sure it's not caught up in any of the other turns there. Pull that through, nice and tight. So there we go. There we have the arrangement. So these are the 3 turns from the with the center tap, and then these are the 2 turns on the other side. So anyway, I'll tin the enamel, get rid of the enamel from the 2-turn side, and we'll get it in circuit. Well, actually, we'll do some continuity testing, then we'll get it in circuit. Okay, so here we go, quick continuity test. So this is the 3 turns. Here's the center tap for the 3 turns, and then this is the 2 turns. So there should be continuity between the 2 turns. And there is, and there should be continuity between all of the 3 turns. And there should be no continuity between the 3 turns and the 2 turns. All right, it's ready to be installed on the board and come right back. Okay, so there's the binocular installed on the board. I'm actually not sure if this method's superior or inferior to the method in the manual, but I guess it's different. You do want to check to make sure that you've got clean solder joints. If you see little holes there, that means you probably haven't removed all the enamel. But anyway, that looks pretty good to me. I'm going to install L4 and come back. Install L4, here it is. So that's 10 turns wound on a T3743. So I've just got to remove the enamel and then get it on the board. Okay, so there's L14 installed. So we're up to the final step now, and that's getting the MOSFETs installed here. And they all go face down, touching the heatsink, and then you put the washer and nut on top of it to keep the connection to the heatsink good. So I'll get those installed and come back. Okay, so there it is. Don't do what I did and put the nut on the bottom. You put the screw on the bottom, otherwise it gets super close to that little C15 capacitor. So anyway, that's that completed, and that's pretty much the board completed. I'm not going to put this PTT jack on just yet. I'm keen to get this, let's put it around the right way. I'm keen to get this on the air, and let's see what we see. Okay, so we're ready to get this on the air and call CQ. As you can see, I've already been calling CQ. I can't help myself. So in all honesty, this isn't the first time I've tried this. So let's call CQ, and we shall see what we see. So I'm calling CQ there. You can see over, I've got the oscilloscope just probing the output there. So I'm on 20 meters. You can see I'm getting around about 34.8 volts peak to peak, and that's with flat out power here, so which is around about 3 watts. I've noticed on 40 meters I was getting around about 4.5 watts, so a little bit of difference there. Oh, I've got an answer, as you can see. Let me just zoom into that answer so you can see it. And it looks like I can barely see that, sorry about that. It's WB9QAA has responded. So let's hope we get a full back and forth here. So we've got to exchange signal strengths, and then there we go. That is at least the first live contact on the air. So one of the things that I just a couple of things to go over on the board. When I first started running it, so this little LED provides some diagnostic information, and I was getting a single flash on transmit, which indicated that although the CAT interface had indicated it was transmitting, there was no audio being received. So I had to basically change the audio settings in WSJTX. I had the digital interface, not the analog interface. So these, let me just pan up to WSJTX so you can see the final settings that I arrived at. Bear with me, sorry for the shaky cam here. So anyway, let's just go back to the settings, file, settings, and then audio. All the radio settings were fine, but these are the two settings you have to have. I thought I did have them, but I wasn't receiving any audio. So anyway, that's first successful first successful live QSO on FT8. Around about 3 watts, as I said. A little bit higher on 40 meters. Let's actually go to 40 meters and see if we can make a contact there. So unfortunately, 40 meters, there's not much activity going on. I will try and call CQ. Here's the waterfall for 40 meters up the top here. Down the bottom's 20 meters. I will try and call CQ, and we'll see if we get any answers. So should be good to go. Let me just pan over to the oscilloscope, and you can see at 40 meters, I'm getting 42 volts peak to peak. So definitely a greater degree of power at 40 meters. But anyway, we'll call CQ, and what I might do if I don't get an answer straight away, I'll kind of pause it until I get an answer, and then we'll. Yeah, there's no answer there. So anyway, I won't bore you all by looking at this. If I get an answer, I'll come back. Oh, and there we have an answer, and it's from KB3RIJ. Thank you very much, KB3RIJ, for your correspondence. Hope we get a full back and forth here. And my antenna doesn't work that well on 80 meters, so we could try 80 meters as well, I suppose. There we go. And that's a full communication. So got a full QSO both on 20 meters and 40 meters. Might let's go up just for yucks and giggles up to 80 meters and see if we have any activity there. Well, it looks like nothing's going on 80 meters at all. The other band we can try is 30 meters. So let's go there, see if there's any activity on 30 meters. Yeah, there's only a little bit of activity. This peak right here on 30 meters. So not much going on there, but good deal. Got a contact on 20 and a contact on 40, and that's great. Let me sort of get off this, and we will just have a look at the board and wrap up. Okay, so this is kind of a wrap up now. I thought what I'd do is rewind this for instead of a 3 to 2 to a 3 to 3. I'm running now on 12 volts. I was running on around about 13 volts before, and you can see. To make sure I'm in a free area. So now when I tune on 20 meters, so less voltage, now I'm getting around about 37, 38 volts peak to peak. And I don't have my calculator handy with me, so but that's probably around about 3.8 watts output. So definitely an increase there. If I go to 40 meters, and just let me wait a bit and make sure there's no one transmitting on that portion of the 40 meters. No, it doesn't look like there's anyone there. So let me tune again, and you can see now I'm getting 49, nearly 50 volts peak to peak, which is significantly more. So obviously that's you do that at your own risk, and Hans says that in the instructions. So anyway. So anyway, this kit's been a lot of fun. I've enjoyed putting it together. I won't sort of I will build the enclosure, but I won't take this video through the enclosure. I haven't really got this, onto the spectrum analyzer yet. I might do that in perhaps a follow-up video. It's been a great, fun little kit. I've enjoyed building it. I hope you've enjoyed me watching build it. Anyway, that's all for now. Catch you all later.